Hello everyone. In this lecture, I'm going to explain relations, binary relations, and digraphs. Basically, we are going to talk about all the materials covered in chapter 5. So we start chapter 5 by introducing binary relations. Let's first define a binary relation. Mathematically, a binary relation between two sets A and B is a subset of A times B. A times B is the Cartesian product of A and B. So any subset of the Cartesian product of A and B can be called a relation or a binary relation from A to B, or between sets A and B. So if you remember the definition of functions in the previous chapter, relations are defined in a very similar way. However, in the definition of functions, we have some extra conditions, but for a relation, we have no extra conditions. So a function is a special type of a relation. So a function is a relation, but obviously a relation is not necessarily a function because it may not satisfy all the conditions specified in the definition of functions. So in order to represent a binary relation, we can use the same representation that we use for functions. That representation is called the arrow diagram. In an arrow diagram of a relation like R, from set A to set B, we have to list all the elements of set A on the left hand side of the diagram and all the elements of B in the right hand side of the diagram. And then if A is related to B by R, this is the way that we represent the relation between A and B, where A is an element of A and B is an element of B. Then you have to draw an arrow from A in the left hand side to B in the right hand side. So I'm going to show you an example in the next slide so you understand how arrow diagrams work. As an example of a relation, you can consider the following relation that we use A to represent it. Relation A is defined in the following way. It is defined between a set of people like P and a set of files. For example, the file can be represented by F. So when we say PAF, it means that P is related to F by A. What is A? Relation A is defined in the following way. If person P has access to file F, so if one person has access to a file, there's a relation from that person to that file, and that relation is called A. This is how we defined relation A. So let's assume that there are three people in our domain. This is called domain in a similar way that we define domain in functions. So Sue, Harry, and Sam. And this is the target or codomain, like file A, file B, file C, file D. In fact, we are studying the access of three people to 4 files. That's why we have only 3 persons in the domain set and 4 files in the target set. So let's assume that A is in the following way. A is a relation, so it should be a subset of the Cartesian product of A and F, right? So let's assume that A is equal to the set of the following ordered pairs. Sue and file B, which means Sue has access to file B. Sue and file C, which means Sue has access to file C. Sue and file D, which means Sue has access to file D too. Harry and file A means Harry has access to file A. And Harry file D, which means Harry has access to file D too. But as you see, there's no ordered pairs starting at Sam, which means that Sam does not have access to any of the 4 files in the target. So If you want to construct the arrow diagram for this relation, what you need to do is you need to list the set of people Sue, Harry, and Sam in the left hand side, and set of files file A, B, C, and D in the right hand side, and connect the person that has access to a file by an arrow. So Sue has access to files B, C, and D, and Harry has access to files A and D, but Sam has no access to any file. Therefore, this is how the arrows are drawn in the arrow diagram of the relation A. So this is how we represent relation A using an arrow diagram. As you see, this is this is an easier to understand representation of relation A than this set roster notation. The relation A defined in the previous slide can be represented by another representation that we call it matrix representation. The matrix representation of a relation like R between sets A and B is a rectangular array of numbers with A rows and B columns. A is the cardinality of set A, the cardinality of domain, and B is the cardinality of the target, which is the size of the target, the size of set B. So in this case, when we have 3 elements in the domain and 4 elements in the target, we can represent this relation with a matrix of 3 by 4 size. So we have 3 rows, 1 for Sue, 1 for Harry, 1 for Sam, and 4 columns, 1 for file A, 1 for file B, 1 for file C, 1 for file D. So as you see, every row and every column has a label based on the elements of domain and target. Now, if a person has access to a file, you need to set the element of that row and that column equal to 1. Otherwise, you have to set that element equal to 0. For example, Sue doesn't have access to file A because Sue and file A is not in this relation. So the element in the Sue row and file A column is equal to 0. However, Sue has access to files B, C, and D. Therefore, the other 3 elements in the row associated to Sue is 1. Sue and file B is 1, Sue and file C is 1, Sue and file D is 1, which means that Sue has access to all the other 3 files B, C, and D. In the same way, since Harry has only access to files A and D, it's in the second row we have 1 in the column for file A and 1 in the column for file D. The numbers in columns B and C in the Harry's row are equal to 0. And as you see, all the numbers in the Sam's row are equal to 0 because Sam didn't have access to any file. So this is how we construct the matrix representation of a relation like A. The next definition in chapter 5 is a binary relation on one single set like A. So far we have seen that a binary relation is defined between 2 sets, from one set which we call the domain to another set which we call the target. But now we define another relation, the binary relation on one set, on a single set. That relation is defined as a subset of Cartesian product of A and itself. So it means that when you only mention one set for a relation, if you associate a relation to only one set, it means that that set is both the domain and the target. So in the previous definition of relation, it means that we have both A and B equal to each other. The set A in these kind of relations is called the domain of the binary relation, and also it is called the target. So both the domain and target are equal to A. And then when you are representing a binary relation on a single set like A using a arrow diagram, then it is possible that one element in the domain is related to itself. In these cases, you need to indicate such relation of one element to itself by an arrow called a self loop. So a self loop leaves the element and then turns around to point to itself again. So the start and end point of the arrow representing that relation would be the same element. That is called the self loop. In the next slide, we'll show you how self loops are represented in an arrow diagram. So let's assume that you have a set like A with which contains 5 letters A, B, C, D, and E, and R is a relation on set A. So R is a subset of Cartesian product of A and A. So this is an example of a relation on A. R contains A and B, B and C, E and C, C and E, D and A, and D and D. So as you see, D is related to itself. Therefore, we have to represent it using a self loop. So this is a little bit different from the arrow diagrams that we have seen before, because it doesn't have two sides. It doesn't have the left hand side and right hand side. Why? Because both the domain and target are equal. So this representation, which we will later define it as a digraph or directed graph, represents a relation on set A. So as you see, since A is related to B, there's an arrow from A to B. Since B is related to C, there's an arrow from B to C. Since E is related to C, there's an arrow from E to C. Since C is related to E, there's another arrow in the opposite direction from C to E. And since D is related to A, there's an arrow from D to A. And finally, since D is related to itself, there's a self loop from D to itself. So this is how a digraph works to represent a relation on a set like A. And then since we have 5 elements in the domain A, there should be 5 points, each one representing one of the elements of the domain. Another important set of definitions regarding binary relations are regarding to the properties of these relations. Let's assume that you have a relation like R that is defined on a set of domain on a domain like A. The relation R is called reflexive if for every element X in domain A, X is related to itself. So in fact, if all the elements in the domain have a self loop, it means that that relation is reflexive. A relation is called anti-reflexive if for every element X in domain A, X is not related to itself, which means that no self loop has to be found in a relation if that relation wants to be anti-reflexive. Another definition is a definition of transitivity. The relation R is transitive if for any 3 elements X, Y, and Z in the domain A, if X is related to Y and Y is related to Z, then X has to be related to Z. This is called transitivity. We have seen transitivity a lot before, like for example in a less than relation we said that if X is less than Y and Y is less than Z, that means X has to be less than Z. Or you can consider a relation like reachability between 2 cities. If city X is reachable from Y and Y is reachable from Z, it implies that X is reachable from city Z. So the concept of transitivity is very familiar for all of us, but this is the formal definition that you need to remember. Then we define symmetry of a relation. Relation R is symmetric if for every two elements x and y in the domain A, x is related to y implies that y is related to x. So if there is a relation from x to y, which means if there is an arrow from x to y, there should be another arrow in the opposite direction from y to x. If a relation has this kind of property, that relation is called a symmetric relation. Then we define an anti-symmetric relation. A relation R is anti-symmetric if for every two elements x and y in domain A, x related to y and y related to x implies that x and y are equal. In other words, if you consider the contrapositive of this relation, if this definition, if x is not equal to y, then either x is not related to y or y is not related to x. Again, what does anti-symmetric means? It means that if you have two distinct elements in the domain like x and y, either x is not related to y or y is not related to x. This definition that I just mentioned is the contrapositive of this relation that is mentioned in the book. So if you look at the Zai book, you can see both versions of the definition, and then you can use whichever that you feel more comfortable with. Here are three examples of relations and their properties. Let's look at the first example. As you see here, we have a relation represented by a digraph. In all of these three examples, the domain A is equal to a set of 5 letters A, B, C, D, and E. In the first example, the relation is reflexive because all of the elements in the domain have self-loops. The self-loops are marked by blue color. And in the second example, you see a relation that is anti-reflexive. Why? Because for every element x in the domain, x is not related to itself. In other words, this graph is anti-reflexive because there is no self-loop in this graph. And finally, this third example represents a relation that is transitive because for every three elements x, y, and z in the domain A, if x is related to y and y is related to z, then x is related to z too. For example, consider this arrow. E is related to A, and A is related to B. Based on the definition of transitivity, E has to be related to B too. As you see, there should be a triangle between E, A, and B. This triangle exists, and that means that the definition of transitivity is not violated by these three arrows. Also, you can see that E is related to B and B is related to C. That means, based on the definition of transitivity, there should be an arrow from E to C, which exists. Therefore, this triangle also doesn't violate the definition of transitivity. Also, E is related to A and A is related to C. That concludes that E has to be related to C, which is, in this case, true. Therefore, the triangle EAC doesn't violate the definition of transitivity too. And then finally, A is related to B and B is related to C. that means that A should be related to C if we want to have a transitive relation. In this case, we have an arrow from A to C, therefore again the triangle A, B, and C does not violate the definition of transitivity. Since there is no counterexample to the definition of transitivity, we can say that this relation R is transitive. Also, in this example, you see that we have a graph that is representing a symmetric relation. Why? Because for every blue arrow that you see in this graph, there's a green arrow in the opposite direction. And that means that the relation is symmetric, because for every two elements, x and y in the domain A, if x is related to y by the relation, then y is also related to x by the relation. For example, since there's an arrow from E to A that is marked with blue, there's another arrow in the opposite direction from A to E. For the arrow from B to A, there's another arrow from A to B. For the arrow from B to C, there's another arrow from C to B. That means the relation is symmetric. This is another example that shows an anti-symmetric relation. Why? Because for every two distinct elements of the domain that you pick, it's not the case that both elements are related to each other. In other words, there is no such pattern that you see at the end of this slide in this graph. So there is no two vertices or points in this graph that are connected to each other bidirectionally. If there's a relation, the relation is unidirectionally. There is no bidirectional relation between any of these two nodes, therefore the relation is called anti-symmetric. So we have seen that one of the ways to represent the relation on a set like A is to use a directed graph, but we haven't seen the formal definition of a digraph or a directed graph. Here is the slide in which we explain the formal definition of a digraph and some of the terminologies that we use later in this course. So what is a digraph? A digraph or a directed graph consists of a pair of two sets V and E. The set that we represented by capital V is the set of vertices, a set containing a number of vertices. Every element in that set is called one vertex for the digraph. And E is the set of directed edges for this digraph, which is a subset of Cartesian product of V and itself. What does it mean? It means that E, which is the set of directed edges, is the set of ordered pairs, and those ordered pairs are constructed by two vertices. For example, if you have an ordered pair like A and B are both vertices in that directed graph. So let's assume that you have an edge like U and V. The vertex U in this edge is called the tail of edge U and V, and vertex V is called the head of that edge. So if the head and tail of an edge are the same vertex, then the edge is called the self loop. So if you have D and D in this case, then that edge is called the self loop. The indegree of a vertex is the number of edges pointing into it. So the number of edges which have a vertex as their as their head are called the indegree of that vertex. the out degree of a vertex is the number of edges pointing out of it. So the number of edges which have a vertex as their tail is called the out degree of that vertex. So let's assume that you have a graph like G equal V and E. V is a set of all vertices containing 4 elements A, B, C, and D, and E is the set of 4 ordered pairs A and B, B and C, A and C, and D and D. So it is very similar to what we have done for representing a relation. All you need to do is to connect is to first represent the elements of the vertex set by 4 points A, B, C, and D, and then connect A to B because there's an edge from A to B, connect B to C because there's an edge from B to C, and connect A to C because there's an edge from A to C, and connect D to itself because there's an edge from D to itself. Because D and D is an element of the edge set. So in this edge, A is called the tail, B is called the head. Okay, and the indegree of C is 2 because C is the head of these two edges, B to C and A to C. The out degree of B is 1 because there's only one edge going out of B. And the indegree of D is also 1 because there's only one edge pointing to D. Next, we define an equivalence relation. A relation like R is an equivalence relation if it is reflexive, symmetric, and transitive. So if a relation has all of these 3 properties, it is called an equivalence relation. Let's assume that A is a set of 6 letters A, B, C, D, and E. I'm sorry, A, B, C, D, E, and F. And R is a relation on A, which is represented by this digraph. As you see, this relation is reflexive because every node has, or every vertex has a self loop. It is symmetric because for every edge, there is another edge in the opposite direction. And it is transitive because for every 3 elements, the domain, if like x, y, and z, if x is related to y and y is related to z, then x is related to z. In other words, it is transitive because we have a complete triangle between A, B, and E. As you see, since E is related to A and A is related to B, E should be related to B, which is true in this case. And you cannot find any counterexample for the definition of transitivity in this graph. However, if you connect E to D in this using this this purple arrow, this dotted purple arrow that you see here, then you can find a counterexample for transitivity. For example, you can say B is related to E and E is related to D, but B and D are not related. So by drawing that purple arrow, we can find a counterexample for transitivity. But if there's no purple arrow here, then this relation is transitive, and since it was symmetric and reflexive, we can say R is an equivalence relation. So let's see more properties of an equivalence relation. First, we're going to define an equivalence class for an equivalence relation. Let's assume that A is the domain of an equivalence relation and A is an arbitrary element of that domain A. Then we can define the equivalence class of A in the following way. The equivalence class of A, which is represented by this symbol in open and close brackets, you can simply write A. That represents the equivalence class of A. This class is defined to be the set of all elements like X in the set A, such that A is related to X by the equivalence relation. So all the elements that A is related to them by the equivalence relation construct the equivalence class of A, and this is how we represent that class. In open and closed brackets, we simply write A. There are two important theorems that are not hard to prove. The first one says, if you have an equivalence relation like R on a set like A, and X and Y are two arbitrary elements of the domain A, then if X is related to Y, you can say the equivalence classes of X and Y are equal. And if X is not related to Y, then the equivalence classes of X and Y are disjoint, which means their intersection is equal to the empty set. So it's important to know that the equivalence classes of different elements in the domain of an equivalence relation are either equal, in this case, or they're disjoint. This is a very important theorem that we can prove, and we will prove it either in the long assignments or in the exercises in the book, but we're going to prove this, and I'm going to share the proof with you so you understand this theorem completely. The second theorem that is very important is that an equivalence relation defines a partition on its domain. So assuming that you have an equivalence relation over a domain like A, the set of all distinct equivalence classes define a partition of set A. You know what partition is. We have defined it previously in chapter 3. A partition of a set is a set of subsets of that set that are non-empty, mutually disjoint, and they all cover the original set A. So the reason that we use the term distinct here is that if there are two equivalence classes that are equal, we only consider them once in the partition. So if you remember, we said repetition in a set doesn't matter, so you can even eliminate the word distinct and say the set of all equivalence classes of a equivalence relation creates a partition for the domain of that relation. In the next slide, I'm going to show you some example. So let's assume that A is equal to the set of all elements A, B, C, D, E, and F. And R is an equivalence relation defined on A that is represented by this digraph. We have seen this digraph before in the previous slides. So what does it mean when we say an equivalence relation defines a partition on set A? It means that these three elements A, B, and E are fully connected to each other. As you see, there's an arrow from any element to any other element in this triangle, and the subset A, B, and E is one of the subsets of domain A that participate in the partition of set A. Another subset that participate in the partition is D and F. The last subset is C. So this relation, this equivalence relation, define the following partition on A. A, B, and E is the first subset in the partition. D and F is the second subset, and C is the last subset in the partition. If you want to do it as a homework. It's it is highly recommended to do it. If you find out the equivalence classes of A, B, and E, all of the equivalence classes that I mentioned for A, B, and E are equal to the first set in the partition. All the equivalence classes associated to D and F are equal to this set, the second element in the partition. And the equivalence class of C is only this set. So it is highly recommended that you write down the equivalence classes for all of these 6 elements in this set so that you understand the last 2 slides in this video.